All right, and we are back with virtual school. This will actually be the last week of lectures, so the last week of new material. We have this lecture, and then we're going to do another lecture on Wednesday, Thursday, and then we'll start a lab on Friday. It's going to be another virtual lab online. It might take a little bit longer than the other virtual lab we did, so I'm guessing we'll probably do Friday and then Monday, Tuesday in lab. And then we'll have our last test on acids and bases. It'll again be an open book, open friend, everything test, and that'll be it for long term. So the what we're going to go through today is kind of the first real world applicability to what we've learned in our acid base units so far. We're going to talk about how to calculate the pH of real solutions, and we're going to go through kind of in detail how to do pH calculations for any strong acid, strong base, weak acid, weak base. But then I'm going to kind of give you kind of a shortcut way to get it. But I am going to go through how this all is derived kind of at length. So put me on ×2 and get through this lesson, but hopefully by the end of it, it'll make sense of how to calculate the pH of real solutions. So we're going to start with the easiest types first, and then we'll get progressively harder. I think the easiest one to understand is a strong acid. So hopefully you can think to yourself, when I say strong acid, what that actually means. And so hopefully you remember that an acid in general, we're using the Bronsted-Lowry definition. So an acid in general is just a proton donor, an H+ donor. So in order to be a strong acid, that just means you're a really good proton donor. So for a strong acid, if we start with our generic acid HA, and you put that in water, so I'll make it aqueous, you're going to come to some sort of equilibrium where you have protons now free in solution because they've been donated, and then you'll have this A-, which would be our conjugate base in this case. But if it's a strong acid, just remember what that means. It means that this equilibrium is not going to be very equal from the reactants to the products. It's going to very heavily favor the products, right? We're going to basically take all of that original acid and dissociate 100% of that acid into H+ and A-. Okay? So what I want you to be thinking about during this lecture a lot is, if we're trying to get the pH of these real solutions, what your ultimate goal is really to get something on that pH square that we went over last lecture. If you remember, each corner represents a quantity that you can then use to calculate any of the other quantities. We had pH, we had pOH, we had H+ molarity, and OH- molarity. So our goal really in calculating the pH of real solutions is just to get one of those from the pH square, because if you get one, then you can ultimately end up at the pH no matter where you start. Okay? So maybe you can see here how we might arrive at one of those quantities on the pH square, because if we have our acid here completely dissociate into H+ ions and A- ions, well, there's our H+. Okay, that puts us on that pH square. So if we can figure out the molarity of just the H+, we can very easily then get the pH. Okay, so we're going to have to think back a little bit into our stoichiometry knowledge, our mole ratio type of knowledge from way back in order to understand how to do this. But I think once I show you a quick example, it'll be pretty easy. Okay, so just keep in mind that because of mole ratios and your knowledge of stoichiometry, if you know the molarity of your acid, you will be able to directly get the molarity of your H+ ions, and then we can easily get our pH of that acid. Okay? So let's do an example. Let's say we want the pH of a strong acid. Let's say we're going to do 0.15 molar HCl. Okay? HCl is a strong acid. Now, in typical class time, if we were in school, you would probably have to memorize the strong acids, the strong bases. But I'm just going to give them to you. There's only 6 of the strong acids, and they're pretty simple to remember. So I'm just going to list them out. And so if you ever see one of these, then you will automatically just know it's a strong acid. So we have a couple acids with our halogens. We have HCl, HBr, and HI. And then we have 3 kind of random ones. We have nitric acid, HNO3. We have perchloric acid, HClO4. And then we have sulfuric acid, H2SO4. So those 6 acids are what we're going to consider strong, and that just means that they 100% will donate their protons, and you can kind of use this method that will be the simplest method in order to get the pH. Okay, so for our first example, we're going to do the pH of 0.15 molar HCl. So what this means is we'll have HCl in solution, so aqueous, and then all of that acid is going to dissociate into protons, aqueous protons, and chloride ions, because that is the anion here. Now, this is a balanced chemical reaction, right? It's just an equilibrium because we're just putting it in water, but you can think of it as a balanced chemical reaction. And if we have 0.15 molar HCl, what would be the molarity of H plus ions given the mole ratio between these two? It's a 1-to-1 ratio, so therefore we can assume that it's also going to be 0.15 molar. Well, we just got the H plus molarity. All you have to do in order to get the pH of this solution is take the negative log of 0.15. If you plug that into your calculator, you will get a pH of 0.82. Okay, so it's a really easy way. All you're doing is you're dissociating 100% of the acid into protons and the anion. They're going to be the same concentration here, and so you just plug that into negative log. Okay, let's do one more. I'll just show you, I just want to show you this kind of odd one because it's the only strong acid that we're going to use that has multiple protons. So let's say we want the pH of 0.02 molar sulfuric acid. Okay, and you might think to yourself, well, this might be different because there's 2 H's here, so maybe there's going to be 2 protons donated, but it's not. We're going to have our H2SO4 in water. All it's going to do is donate 1 proton, so you have your H plus, aqueous, and then you have HSO4 minus as your conjugate base. And the molarity is going to be the same again because it's again a 1-to-1 ratio. If it's 0.02 molar here, it's also going to be 0.02 molar here. You plug that into our pH equation, negative log of 0.02, and you get a pH value of 1.70. Okay, so strong acids are very simple. They'll act like this 100% of the time. Okay? Let's go on to our second type, which will be strong bases. These will be a little trickier, so that's why I put them second. They're a little trickier because this will be the only time throughout this entire unit that we're actually going to use the Arrhenius definition of a base. And if you remember what the Arrhenius definition was, it's anything that you put in water and it increases the concentration of OH minus ions. okay? Basically, we said to be an Arrhenius base, you had to have hydroxide in the compound, okay? So basically, you can think of this reaction, this generic reaction, where we're going to have a compound that looks like this. I'm just going to put B here as our generic cation, but it will always be connected to this OH minus hydroxide ion. If we put that in water, you can think of it just as a regular old ionic compound. And what happens when we put ionic compounds in water is they split up into their ions. And so what this is going to do is split up into our cation, which will be aqueous, and our hydroxide ions, which will also be aqueous. Now again, remember, if we're trying to get the pH of a solution, you just want to try to get something on that pH square. Well, luckily, the molarity of OH minus is on our little pH square. If we get that, we can take that kind of roundabout way up to pH and very quickly calculate it. So let's try one of these. Again, I'll just give you strong bases are always, in our case, we'll just simplify it. It's going to be anytime you have a group 1 or a group 2 metal paired up with hydroxide. Okay, so we say group 1 and 2 hydroxides are going to be our strong bases. So that's like sodium hydroxide, lithium hydroxide, barium hydroxide, strontium hydroxide. We're just going to put every metal from the first 2 columns in our periodic table. If they're paired up with hydroxide, we'll consider it a strong base. Okay? So let's just do let's do a tricky one just to show you. It's going to be the similar setup to an acid, but I just want to give you an example of where this could get just a little tricky. So let's do 0.25 molar strontium hydroxide. So strontium is in the second group, so it's going to be our strong base, but it's got a +2 charge. So we're going to have to pair it up with 2 hydroxide ions because each hydroxide ion is only -1. Okay? So if you plug this into our kind of generic equation of what's going to happen, you can hopefully see that if this dissociates into its ions because it's an aqueous solution, we're going to end up with Sr + 2, and that's aqueous. But then we have 2 hydroxide ions. They're going to split up independently. So you're going to have to say that we have 2 OH minus ions. And now, unlike the ones with our strong acids, now this will not be a 1-to-1 mole ratio, right? Now it's going to be a 2-to-1 mole ratio. If you think about how you would set up those fractions when doing stoichiometry and setting up that mole ratio, if we're trying to get to OH minus, the 2 would be in the numerator. We're trying to get rid of SrOH2, so that would be in the denominator. So it would be a 2-to-1 ratio. So all that means is if you have 0.25 molar of strontium hydroxide, when that dissociates into its ions, because there's 2 hydroxide ions for every 1 strontium hydroxide compound, we're just going to double that molarity. So instead of 0.25 molar, it's going to double and become 0.50 molar OH minus. Okay? So if we have that, we could easily just plug that into our equation for the POH. If we do the negative log of 0.50, if you plug that into your calculator, you should get an POH of 0.30. A very, very low POH means it's very basic. And if we want to turn that into pH, you just subtract that from 14, right? Because the pH and the POH always add up to 14, and you would end up with a pH value of 13.70. Again, very basic. All right? So strong acids, strong bases, just think about complete splitting up of that ionic compound. For an acid, it would be H plus and whatever anion it's connected to. For a base, it's going to be whatever cation it's connected to. It's going to be a group 1 or 2 metal, and then it's going to be your hydroxide ion. Okay? Just pay attention to that mole ratio because you might have to multiply it depending on how many hydroxide ions you have. All right. This chemistry lecture brought to you by the memories of going places. Do you remember going places? Places. We're back. So we're going to now start what I think is my favorite type of calculation for real solutions. And just before I started filming, I said to my wife, this is my favorite. It's fun to do weak acids. And her response, and she's also a chemist, and she said, yeah, it's really fun. So maybe I'm the only one that thinks it's fun, but it kind of sucks to have to give this lecture to a computer and not be able to see all of your beautiful confused faces in the audience. But we'll try our best and get through this. So weak acids are a little more difficult to work with, but just remember what we mean by a weak acid. Okay, so to be a strong acid, it means you're really good at donating a proton, but a weak acid, it's kind of a crappy proton donor, right? So if we have our acid again, HA, and it's in equilibrium with this dissociated proton and A minus, all we're saying is that not much of this HA acid is actually going to dissociate into H plus and A minus. Most of it is going to stay as HA, and just a little bit is going to go to H plus. Okay? Now again, to get the pH of these solutions, we are trying to get something on our pH square. Well, this H plus is again going to be what we're trying to get because that will let us easily calculate the pH. It's just going to be a little more difficult because we can't assume that all of the HA dissociates, so we're going to have to try to figure out exactly how much HA, our acid, dissociates. And in order to do that, we're going to have to relate it to our equilibrium knowledge, right? Our equilibrium will tell us how much of the reaction goes forward, how much of it goes backward at equilibrium, and where it's poised. So in order to do that, just think about our equilibrium constant. Remember, for acids, we call our equilibrium constant Ka, and in this case, it will just be the molarity of H plus times the molarity of our A minus ion all over the original molarity of HA. Okay? So if we can use this, our Ka equation, to get that H plus concentration, then we can very easily get the pH. What we're going to have to use are the values of these Kas for acids. So whenever you have to do a pH calculation of a weak acid, you will always be given the Ka value for whatever acid we're working with. Okay? So to do this, I think it's easiest to see an example kind of in action while we teach the method of how to do weak acids. All right, so for our example, I'm just going to erase this because we're going to need a little bit of space. For our example, we are going to try to calculate the pH of 1.25 molar carbonic acid. Okay, and carbonic acid has a Ka value. Our equilibrium constant will be 4.5 times 10 to the negative 7th. So it's a really tiny number, which just tells you that it's going to heavily favor the reactants in this reaction. We have H2CO3 in equilibrium with H plus and HCO3 minus. This Ka value says that we are going to heavily favor this H2CO3 side of the reaction. Okay? So our Ka equation is going to be H plus ions times HCO3 minus ions, or the molarity of those ions, all over the molarity of carbonic acid. And if we can solve, and we know this equals 4.5 times 10 to the negative 7th. So our goal is going to try to solve for that H plus molarity, okay? Now, again, we have to think about it at equilibrium. So we're gonna have to do a little math here to figure out what it's going to be, but I think it's pretty simple, okay? So what you're going to do is set up what we call an ice table. An ice table will help us get these molarities at equilibrium. And so in order to set up an ice table, I'm going to have to do it a little tiny over here. Across the top of your ice table, you're just going to put the molarities of each species you have in your reaction. So here we have H2CO3, here we have the H plus molarities, and the HCO3 minus molarities. So across the top row, that's what you're going to put, all substances that are in your reaction. And then down the column, you're going to spell out ice. And each of those letters stands for something different. So I, in this case, will stand for the molarity initially, okay, before any dissociation has occurred. So what we're assuming is that basically we put an acid in water, and before we allow it to do what an acid does, which is dissociate and donate that proton, before we allow that to happen, it's the molarities initially. So that's what we're going to consider the I row. Then the C is going to stand for the change. It's going to represent what has to change in order for this acid to get to equilibrium. And then the E stands for what the molarities would be at equilibrium. Okay, so ICE, initial, change, and equilibrium. Okay, I just don't have enough space to spell it all out, but that's what it stands for. Okay, so let's fill in the first row for initial. Again, the initial means before we let any of this reaction occur. So we have 1.25 molar H2CO3. We have not let any of that split off into H plus and HCO3 minus. So our molarity of our original acid will be 1.25 molar, okay? Again, no acid has donated a proton yet. It is all in the form of H2CO3. Having that said, hopefully then you could fill in the molarities of the other side of the reaction. Well, we haven't let the reaction occur yet, so these are just going to both be 0 initially, okay? Now, the C row is the change, so now we're going to let this reaction occur. In order for it to get to equilibrium, what reaction is going to have to occur? Well, it's going to have to be the forward reaction, right? We're going to have to produce some H plus and HCO3 minus. It's not going to be a lot because of a tiny, tiny equilibrium constant, but some of it's going to happen. So we don't know exactly how much acid dissociates, but we know some of it is going to be lost to H plus and HCO3 minus. So because we know we're going to lose some of our original acid, but we don't know how much, all we're going to do is we're going to say we're going to lose X amount of that acid, H2CO3. Look at your balanced reaction here. It's all 1 to 1 to 1. So if you lose X amount of acid, you're going to produce that same amount of H plus and HCO3 minus, right? Because whatever you lose here, you have to gain here. So we can just put this as plus X and plus X. Now for the equilibrium, so that's the change that would have to occur to get to equilibrium. The equilibrium row is basically just adding up the first two columns, or the first two rows in each column. So at equilibrium, our H2CO3 will be 1.25 minus X, minus whatever amount of acid we lose. At equilibrium, the H plus ions will be just X, because that's how much H plus we gained during this process, and that will be the same for HCO3 minus. So we have our Ka equation, we know what it equals, and now we can plug in these values because this is what it would be at equilibrium. So if we go ahead and do that, we will plug in X as our H plus molarity. We'll plug in X as our HCO3 minus molarity all over 1.25 minus X, and that's going to be equal to 4.5 times 10 to the negative 7th. Okay, now here comes a little shortcut. Now, you could solve this, right? This is an equation with one variable, it's just X. So you could actually go ahead and solve this. If you see, you'd have X squared in the numerator, so it would end up being a quadratic formula. It's kind of a pain in the ass to do that, but you could go through and solve for X. But think about what a weak acid means. It means that not much of your acid is going to dissociate. So if we start with a fairly high molarity, and in terms of molarity, 1.25 molar is a really big molarity. If we start with a relatively big number and then we lose just a little tiny amount of that acid, well, you have a large number and then you're subtracting a really, really tiny number, you're basically going to end up with that same exact large number. It's not really going to change. So what we can actually do here, and this will be the case for all weak acids, is you can actually just ignore that minus X. We're just going to pretend like it's not even there, and it just becomes, if you do that, it just becomes X squared over that original molarity of your acid, and that's going to be equal to the Ka value, 4.5 times 10 to the negative 7th. Now this is even easier to solve, right? You're going to multiply both sides by 1.25, take the square root, and you'll get an X value that's equal to 7.5 times 10 to the negative 4th. Okay, and remember, what is X? What did we designate as X here? Well, X represents our H plus molarity, and that's great because once we figure that out, that puts us right on the pH square. This is our H plus molarity. Hold on, the dog wants to go out. Go ahead. That is our H plus molarity. That puts us on the pH square. Plug that into negative log of that number, and you will directly get the pH equal to 3.12. All right, last one, and this is, I think, the trickiest just because there's kind of the most steps that you have to go through in order to get to the pH, but this is going to be a weak base that you're trying to get the pH of. Weak base, remember, we're just going to have to think of it in this generic form where we have our base, and I'm going to have to put plus water here. It's really just you're putting your base in water to dissolve it, to make it aqueous, but that's going to be our acid in this case. So I'm going to show it in this case because we have to show where this H comes from to our base. The water is going to donate the proton to the base to become Hb plus, and then we will end up with OH minus. And again, remember your goal is just to get something on that pH square. Well, if we can get the molarity of our OH minus according to this reaction, then we can go around the square to the pH. This will be aqueous, this will be a liquid. So in order to do this calculation, we're going to have to use the same concept that we just did for weak acids, setting up the equilibrium expression for this base in water. And so remember, you're only using aqueous and gas, aqueous solutions and gases in your equilibrium constant, so we will not have the water. Just like for a weak acid, water was present, but it's not going to be in your equilibrium constant either, so we don't even have to list it. So I'm going to put our Kb is equal to our Hb plus molarity, that would be our conjugate acid, times the OH minus molarity, conjugate base, all over the molarity of our base. Okay, so that's going to be the general setup, just like we did for Ka. I'm going to show you a real example just to go through the steps. So for this one, we're going to do the pH. I'm going to erase this. So for example, we're going to do the pH of 4.5 molar ammonia, NH3. It's like the most typical weak base I could choose. It's got a Kb value of 1.8 times 10 to the negative fifth. Okay, so that's going to be our Kb value. So we already set up our Kb expression, and we already know what it's going to be equal to. It was 1.8 times 10 to the negative fifth. Now, in order to do this, we're going to have to get these concentrations at equilibrium. So again, we're going to set up an ice table where we have, our ice table will describe this reaction of NH3 in water going to NH4 plus and OH minus. We don't need water in there, so we'll have the molarity of NH3, the molarity of our conjugate acid, NH4 plus, that's just the ammonium ion, and our OH minus. And this is what we really want to get at equilibrium because that will put us on our pH square. Ice, I for initial, C for change, E for at equilibrium. Initially, the molarity of our base is just 4.5. We're going to do this exactly the same way as we did for a weak acid. It's going to be before we let any of this base do what bases do, which is accept that proton. So initially, no base has accepted a proton yet, and so we do not have anything on this right side of the equation, so they're going to both be 0. Now, when we let this reaction get to equilibrium, we're going to have to go from left to right, from reactants to products. So we will end up, just like our last example with acids, we will end up losing some of our original base. For every base that we lose, we will gain one of these ions each. So we will put minus X, because we don't know how much we're going to lose, but we're going to lose some. So minus X from our original base, and then plus X for our new ions that we're forming. Okay? The at equilibrium is just adding up the column. So 4.5 minus X, this will be X, and this will also be X. Then we can come over here, plug it into our Kb equation, which will end up being X times X over 4.5 minus X equals 1.8 times 10 to the negative fifth. Again, the amount of base that we lose to protonation is going to be very tiny. So all we can do is eliminate that minus X in the denominator, and it becomes a much simpler equation. Here would be X squared all over 4.5 equals our Kb value. Multiply both sides by 4.5, take the square root of it to get X, and our X will end up being 0.009. Now remember, in this case, because we're talking about a base, what does our X represent? Well, here, our X represents OH minus concentration. For weak acids, it was the H plus concentration. Now it's going to be OH minus because we're working with bases. This puts us on the pH squared. You're going to have to do a couple steps, but that's okay because we can get the pOH by taking the negative log of 0.009. That pOH would end up being 2.05. Then you can subtract that from 14 because the pOH and pH equal 14 when you add them. Subtract that, and so you should get a pH value of 11.95, which is very basic. Okay, so same with an acid. You set up your little ice table, but you really might not need to, right? Because it's always going to end up being the same thing. You're going to have X squared over your original molarity of your base equal to the Kb. That's it. So if you, you know, for our purpose, you really don't have to set up this equation. You can, or this ice table, you can kind of just skip right to this x squared over original molarity equals your Kb. Solve for x. If you're solving for x for a weak acid, it's the H plus concentration. If you're solving for x for a weak base, it's your OH minus concentration. Keep that straight in your head, and then just go along the pH square, get to pH, and you're done. All right, that's it. Good luck on your assignment.